So yeah, let's start the presentation. Why is it important to understand about mines? Well, we need to become as informed as possible in order to talk to people clearly and accurately about the potential impacts that mines have in our area. And to do this, we need the tools so that we can understand what the studies or evaluations might tell us about potential impacts to the environment. And mine waste and its effluents are one very real consequence of historical and potential future mining in our area. Among other things, Rick will take a look at the problem of mine waste, the true potential for serious environmental pollution from long-term leaching and oxidation of mine waste is a difficult one to assess, but it is critical that we assess it correctly if we want to avoid creating another serious toxic problem down the road. And the magenta drain is a great example of what happens if potentially if things aren't addressed properly at the beginning. So we are very fortunate to have Rick Humphreys with us tonight. Rick pursued his undergraduate and master's degrees in geology at Cal State University, San Jose. Rick comes from a mining family, I just learned, and spent most of his career as a scientist with the State Water Resources Control Board, where he worked on water assessments of active and historic mines. And after retirement, Rick was a science and policy advisor to the Sierra Fund and worked on Sierra Fund's toxic mining initiative. He's also an avid bicyclist. So Rick, welcome. So happy to have you here this evening, and take it away. It's yours.
Thanks, Greg. It's nice to be here. That's quite an introduction, so I hope the talk lives up to it. Anyway, I hope you find this interesting, and for those of you who have worked around mines, it's probably going to be a little too basic, but hopefully it'll fit the bill. Next slide, please. Yeah, this slide kind of introduces the terms that miners use to describe what they're doing, and it's really useful in my mind to understand their terms, so it prevents misunderstandings and helps your credibility if you're using terms correctly. Next slide, please. So while you're thinking about that, I wanted to show you a general schematic of an underground mine in a mountain. First thing I want to point out is that usually there would be a air shaft that went from what's marked as the adit to the mountaintop. And the reason for that would be that that provides air circulation, which is really important in underground mines. Now, before this schematic depicts a mine in production, but before it got into production, the mining company would have to go out and find out if there really was an ore body there. They might have found a surface exposure, or they might have picked it up by geophysics. And if that were the case, they would have to put together an exploration drilling program to determine the size and the shape and the grade of the ore body, and then make a decision on whether the economics were correct, where they could go in and mine this thing. And there's a lot of money that they'd have to spend to do that, because they'd have to put in all the supporting underground workings, ship in equipment, and the whole bit. So before they get any money out of the mine from mining ore, they have to spend an awful lot to just get to that point. So what happens when they stop mining in a case like this is that you can see the rock waste piles on the sides of the mountain. These days, they would probably have to do something with those, like put them in a repository, or they might decide to backfill the underground workings to get lessen the chance of surface subsidence, and to reduce the volume of the potential mine pool in the lower workings. In the upper area, when that gets abandoned, water would continue to drain out the portal, And in the experiences we've had at the water board, that creates a situation where you can have a potentially really nasty effluent. And if that happens, you're looking at perpetual water treatment, where some people like to plug things like this and then promptly retire, because you end up with a plug in the lower adit that's subjected to water under a lot of pressure. So the main points of this schematic are, like one, the company has to spend a lot of money before they even get to go mining. And two, groundwater flowing into the underground workings when mining ceases will fill up the lower below grade, the underground workings below grade, and continue to drain out of the portal in perpetuity. Next slide, please. So this is another schematic. It's more of a mine in the situation of in a flat area. You can see that all the mine workings go down. They've started mining in the upper part of the deposit. They have this open stope that's marked there. And the same things apply here. They would have a lot of expenses to prove out that ore body. They'd have a lot of expenses to access it and start mining it. They have to ventilate the mine, because you can't, you don't get any natural circulation in this sort of situation. And if you don't have compressed air going in there, the miners are all going to suffocate. You have to do one thing the miners hate to do. You have to haul all the ore straight up and out of the underground workings. And then when they cease mining, as you can imagine, the water just fills them up, fills up the underground workings, and you may or may not have a surface water discharge. Next slide, please. So that's the general overview of the kind of the nuts and bolts about underground mining. The next thing you need to kind of be aware of is the kind of mine waste that these mines generate. Number one, we have mill tailings, and these are produced by the processing, the grinding, and this material tends to be really fine grained and uniform form. At new mines, the mining company has the opportunity to characterize the mill tailings and plan for how they want to dispose of them. In old mines, that was never done. So when you find an old deposit of mill tailings, they're usually poorly characterized. I think you've run into some of that here. There are some tests that are used to characterize these sorts of waste. One's called a static test, and it was a test developed in the coal mining areas to determine whether the mine waste would produce acid. And it's a simple bench test where you determine the amount of sulfur in a sample, and you back calculate how much sulfuric acid it'll generate if it were all oxidized. And then you compare that to the amount of calcium carbonate or neutralization potential in the waste, and you arrive at a ratio. And if it's favorable for neutralization, people conclude that there won't be any acid generation and there won't be any problem. Well, as you can guess, that's a pretty simplistic way of looking at things. So there's another type of test that's used these days called a kinetic test. And basically that subjects the potential waste material to accelerated weathering. And these things are done with fairly large volumes of sample in columns or out on line pads. And basically you let the waste weather. Sometimes you speed it up by adding water and running faster cycles, and you monitor the effluent that's coming off, because the waste, that the mine material that's been under reducing conditions until it was mined, well, you want to see how it behaves when it starts oxidizing. So those are the sorts of tests that the companies use these days to characterize that, and then they make predictions on what the effluent looks like. So, if you actually get an effluent out of a kinetic test, that's pretty good information because it tells you what the quality is, and then that goes what the constituents are, and that tells you a lot about whether you can just let it discharge or whether you're going to have to do treatment or anything like that. So anyway, again, at old mine sites, you don't have any of this, so it's very hard to deal with historic mining waste unless they're so reactive that the problem is pretty obvious. So mine waste vary widely in volume and physical and chemical characteristics, and these days there's an effort to try to make sure that they're handled correctly, because when you're dealing with large masses of waste, if you get it wrong, it's very expensive to retrofit any sort of mitigation methods or move the waste. Next slide, please. So these are mill tailings at a modern mine. This is the Jamestown mine. These the tailings are in that big flat area that have the water there. This material was ground up to about silt size and then slurried out into the impoundment. The reclamation plan was to have these things drain out naturally through the tailings impoundment of the forefront, and then the land would be suitable for development. Unfortunately, the tailings didn't really drain, so the surface is unstable and can't really be compacted. And there's sulfide oxidation apparently going on because the effluent coming out of the tailings impoundment is high in sulfate. Now, that's not, it isn't an acidic discharge, but introducing high sulfate into a stream that is rated for cold water fish as a beneficial use is, in the regional board's mind, a degradation. So this mine is an ongoing problem, even though it's closed. Unfortunately, the county released the reclamation bonds, so there's really no money left to address the problems at this old site. So again, the material in this impoundment is fine grained, it's fairly uniform, it doesn't contain mercury, and it was done, it was handled in a way that people thought was going to make it an overall benefit, but it hasn't turned out that way. Next slide, please. So heap leach waste, I'll just go over this really quick. This is the modern way of extracting gold these days. And if you drive across Nevada on Highway 80, you'll see it looks like the Mayans were out there creating all their pyramids, because they have a lot of mines where they use this heap leach technology. And generally what they do is they just mine the ore. They don't have to process it much other than maybe grind it so it isn't huge boulders. They put it on a pad, and as you can see, the one in the bottom of the picture is quite large. They will mix the ore with cement, because the cyanide solution that they sprinkle on the top and run through the pile and then recover has to be in about pH 10. If it's lower, the solution will break down and you'll have a hydrogen cyanide gas release. The miners don't like that, because then the cyanide's expensive and it costs them money. So when they're done doing the heap leach operation, they like to close these things in place. They say, well, there won't be acid generation or anything like that because we put all this cement in here and that'll buffer it. But what people have found out is that, well, actually there's pyrite in these heap leach ores and they do oxidize, and you get an effluent that is neutralized by the cement, but that doesn't drop the arsenic and selenium out. So you end up with effluents that are chemically problematic. But if you ask these guys to move you can see that moving a pile of this stuff to somewhere else is not going to really be feasible. Next slide, please. So waste rock is it's the coarsest material, biggest rocks, and the most voluminous waste that you see at a mine. And waste rock's kind of an interesting term because people like to think that it's waste rock because there's no, it's not mineralized, but oftentimes it is. And the reason it's waste rock is under current economic conditions, there's not enough of whatever they're mining to justify processing. Of course, that can change. I've seen low-grade ore piles turn into waste rock when the price of gold dropped, and that happened not too long ago over at the McLaughlin mine. So anyway, the mining companies just really like to dump this as close to the mine as they can to minimize the cost. The bottom photo shows that with the end dumps there next to those pits. The upper photo shows what happens when the waste rock is determined to be reactive. And that's a waste rock dump at the McLaughlin mine where they've capped the waste rock to prevent it from generating acid. And it kind of does, although there are seeps of really pretty poor quality water. But that has to be maintained forever. And that's what the reclamation bond needs to cover. Of course, the mining company involved there decided that they wanted to donate the property to the UC system as a biological research center, which, when you think about it, is like, well, does the state of California need any more potentially problematic lands? I mean, we already have mine sites that are costing the state a chunk of change because there's pollution involved. But anyway, there's an interesting anecdote about this too that I wanted to share with you. Well, not too many years ago, there was an open pit mine that was proposed, and the miners wanted to dump the waste rock on an area that the Paiute Indians had historic trails through. And it was on BLM land, and the BLM said, okay, miners, go ahead and do it, even though the Paiutes protested. And that was about the same time the California Gaming Compact got signed. So all of a sudden the tribes had money. So they got a bill passed that requires that open pit gold mines get filled back up with waste rock. So a situation like what you see in the lower photograph isn't supposed to happen anymore in California. So I thought that was pretty interesting turnaround. So anyway, the problem with this waste rock is, like I said, if you're wrong on the characterization and it starts becoming a problem, it's pretty hard to do anything about it, especially if the company that was mining sort of dissolves and their parent company is a company in Canada somewhere. Next slide, please. Overburden, this term is often mixed up with waste rock. Most people like to think of overburden as the soil you're going to use for revegetation, but it really should be tested because sometimes it's mineralized, and if it is, it's not going to work very well for reclamation and may even cause a problem if you use it for reclamation. And there are examples of that happening at mine sites. Next slide, please. Okay, I put this in just to give the miners a break. Dredge spoils, like for channels, can also cause an acid discharge. And because the sulfide in them is so poorly crystalline, it happens really fast. The Dutch know a lot about this because they're dredging in the North Sea all the time. Next slide, please. So, you know, everybody's probably got the idea now that it takes a lot of sampling to sort all this stuff out. And it's a lot like characterizing what the miners do to have to characterize the ore. You know, they want to make sure that they have an ore deposit that they can mine at a profit. And so, you know, they work really hard at it, and they have all these interesting statistical models to tell them, you know, what the shape and the size and everything else is about the ore. And then they take the ore and spend a lot of time processing it to figure out how to get the most gold out of their rock the cheapest way possible. And that's the kind of the same thing that we like them to do for the wastes. We really want to kind of know how these things are going to behave. And the samples that the miners collect, like surface and grab samples and trench samples, you know, the exploration drilling samples, and the metallurgical testing, that's going to provide the information to determine how the waste ought to be handled. Next slide, please. So there's some more of the, during the mining, you know, there's always a chance that your initial characterization of the ore body was wrong. Heaven forbid. If it's wrong in the, that there's more gold than you thought, well, great, but sometimes it goes the other way. Those are also useful in characterizing the waste because, you know, as with ore, the mine waste that comes out later in the operation might be from a different rock type and might be mineralized differently. And you need to know when if changes like that occur pretty much as soon as it's happening, so the waste can be handled accordingly. Next slide, please. So a summary of this is, well, you know, testing programs result in a lot of samples, and, you know, predictions based on early testing may change. It's just the way it is. And then predictions based on early testings, well, they really need to be reviewed as mining continues. That's 20. Next slide, please. Okay, does everybody want to take a little breath here, and then I'll start the third talk? Thumbs up. Okay, so this is from a class that a bunch of us put together before I retired, and you know, it was based on predicting whether acid generation would occur. And so I figured an overview of this would be useful. And please keep in mind that acid generation, even though it is described in De Re Meticulous, and that's the book that Herbert Hoover translated from the Latin. It's like a 13th century book on mining from Germany that was written in Latin. They describe acid mine drainage. You know, they talk about the mine waters that if their cattle drink it, they die. So, you know, this is not new, but it's still an area of active research, and it's pretty interesting when you delve into it. But so since it isn't new, that means it's been around for a long time. And so the question you always ask is, well, why do we care? I mean, you know, so next slide, please. Well, because it causes really serious water problems. It can cause fertility problems, you know, if it happens in your 40 hectares that you just drained in Holland, for your sunflowers. If the soil all turns to pH 2, they're not going to grow. And, it's really costly to clean up. I mean, we're looking at Superfund sites that are going to need water treatment for over 1,000 years. I mean, it's a serious deal. So I imagine we all agree on the bad. Next slide, please. But there's some good aspects to it, and some of you get to see it tomorrow because I have some show and tells. But acid generation under natural conditions occurs at rates that are, 1,000,000 times slower than what you see when we accelerate it by creating a perfect reactor in an underground mine. And this process enriches ore bodies by leaching the top parts as they're brought up to the surface and eroding, and transferring the elements that people like to mine, like copper. It carries them down to the redox boundary, where you go from oxidation to reducing conditions, and it deposits the copper there. So, and that's called the enrichment cap on these deposits. And instead of looking at ore that's like 1% copper, you're looking at ore that's maybe 20% copper. And not only that, it's 1,000 feet thick and covers maybe 5 square miles. And that's all from these fluids that migrate down. Butte, Montana is another one. They had a supergene cap that was pure copper and 4 feet thick. And, the top of that Butte mountain is a couple square miles. So it's an important natural process to us. I mean, we wouldn't be able to mine a lot of these deposits because at current prices, because they wouldn't have enough commodity in them. It produces iron-rich soils sometimes, and it makes really cool crystals. You can see the little guy in there with those gypsum crystals. Those things are crystallized from enriched fluids. They were high in sulfate from pyrite oxidation. Next slide, please. So what do we see this problem in? Well, coal, I mean, that's where some of our testings come from. Marine sediments, I mean, we've talked about that. Got metamorphic rocks. If you look around Nevada City, you'll see a lot of rock walls that have all this iron staining on them. Well, that's from pyrite oxidation in the rock. Iron sulfide rich sedimentary rocks. You think we have any up here?
Yeah.
Well, we do. Those hydraulic mine channels that were all the hydraulic mines were, the blue leads they talk about, they're blue because that secondary iron sulfide that formed in the bottom of the channels after they were capped. And, if under the right conditions, you can get acid drainage out of these mine pits. And then hydrothermally altered rock, well, that's, gold mines. So next slide, please. So this is a list of the minerals, sort of in the order of the fastest oxidizers to the slowest. We have other sulfide minerals, and they don't really oxidize to form acid, but the ferric iron produced by iron sulfide oxidation can cause them to oxidize, and that's how you get the metals in the discharge. So, next slide, please. Okay, so all you chemistry buffs, I knew you'd like to see this. This is pyrite oxidation with the biological component included. You see at the very bottom, that's the step where you have the iron that was already oxidized by the bacteria going and re-oxidizing new pyrite, without any oxygen. and creating an awful lot of acid. But a bit easier way to take a look at this is in the next slide, please. So this is a schematic, which is a little bit easier to follow. You have your pyrite in the center, and to get it started, you need oxygen, water, and then you have the thiobacillus for oxidants. And those little guys get going in a way that where the first product you get is ferrous iron and sulfate and hydronium ion. So that's sulfuric acid. And then the thiobacillus oxidizes the ferrous iron to to ferric iron, and that creates more acid. I mean, generally, when you see water that's ferrous iron stable, it's pH 3.5, and when you see it ferric iron stable, it's pH 2. So it's an order of magnitude more acidic. And then the ferric iron can go back up and oxidize the pyrite or the other the other sulfides around. So you can see that this is a do loop. And once it gets going, what's really going to matter is that you got a lot of pyrite. And, if you do, you're going to get more bacteria as this keeps going. And that's why there's like a time lag. But, once they get going, I mean, you get situations like in Iron Mountain mine where it's oxidizing so vigorously, the mine is like 120 degrees because, pyrite oxidation is exothermic. So next slide, please. So just to show you that all iron sulfides are not equal, these specimens are from Spain and down near Jackson, respectively. This is stable pyrite, well crystallized, not oxidizing. Stuff's about 60 million years old. Next slide, please. Well, this is a 300 million year old chunk of pyrite from Iron Mountain mine. It's oxidizing in my backyard. You can see the crust of salts on the surface. Those are iron sulfate salts that when it rains, or those are really soluble, and they'll. That's why you see these mine sites when it rains and you get a flush of water out of these underground mines. It's often really toxic and really acidic because those iron salts hydrolyze. Next slide, please. So there are some secondary causes. The rapid release of acid from, say, for instance, an old waste rock pile or the underground workings of a mine that's been abandoned for 100 years. You have salts like melanterite, rosenite, and all these things. And they just go right into solution, and you end up with a mine water discharge, pH 1 or 2. The slower acid producers are like alunite and jarosite, and they're the minerals that form what we call gaussins on the tops of ore bodies. That I'll show you a piece if you come on the tour. I brought some show and tells. So typically in a waste pile situation, you have the waste pile gets wet, and you get acid generation. You may or may not see a discharge. But as it dries out, you get these salts forming. So the next time it rains, it starts generating acid again. Meanwhile, you flush the salts, and if the rain's heavy enough, you can see a pretty acidic discharge from an old pile. The same thing happens in an underground mine. When it rains, the water volume comes flowing through really fast, dissolves a lot of salts, and you end up with a pretty toxic discharge. Now, when people say they want to plug a mine to stop the mine water from coming out, the water can back up in the underground workings, and you end up with a situation where there's a lot of pressure on the plug. Plus, if you'd plug because there was acid generation going on, you'd end up with a mine water pool that was pretty acidic because you dissolved all these soluble iron sulfate salts. So you'd have a situation where you have a plug under high head backing up water that's pretty chemically aggressive, and you have to keep track of it forever. So let's go to the next slide. So this is what it looks like in Iron Mountain. These pretty minerals are the iron sulfate minerals that we find in the mine. I've taken some of this stuff and dissolved it in water for elementary school classes and then dumped in baking soda, and it looks like a volcano erupting. Next slide, please. And these are some of the extreme end member minerals you get. If you look at the rhomboclase carefully, you'll see that it's essentially crystalline sulfuric acid. And these two are both from Iron Mountain Mine. Next slide, please. So here are the iron sulfate minerals for all of you people who want to have some good Trivial Pursuit information. Next slide, please. So the natural buffers we have available to us, or nature has available, is calcium carbonate, and that'll buffer acid pretty fast. Of course, the best one is calcite, and they get progressively less effective as you go through from dolomite to magnesite to anchorite. But the thing is about the buffering is this is just a straight old chemical contact to contact reaction, and you can't really expect this kind of thing to control a biologically catalyzed reaction because the rates are really out of whack. So a lot of times what happens, there's so much sulfate that's being produced by the carbonate mineral neutralization that it coats the minerals that are supposed to do the neutralization. So it's much less effective than what you calculated it out to be. The other kind of neutralization you get is with silicates like feldspars, but that's pretty slow. And if you've got any kind of fast acid generation going, the silicates are just not going to cut it. Next slide, please. You can find this phenomenon going out if you just take a drive up Highway 49 and keep your eyes open. These are iron sulfate salts that are forming on a road cut that's rich in pyrite on Highway 49, somewhere near the town of Downeyville. And then next door you have iron sulfate salts forming on pyrite that's at the surface at the Iron Mountain Mine. And when it rains, what happens is the rainwater dissolves that stuff and it goes into a culvert, and you get a little discharge into the river. It probably won't kill any fish, but it's a source of acid loading. Next slide, please. So a bunch of us were kind of brainstorming. We came up with this summary because it's hard to generalize about this phenomena. So we said, well, yeah, you have situations where you have a massive pyrite and it really oxidizes fast, and it causes big problems. And there's some reasons we think it oxidizes fast, but as I said, this is an area of research, so we'll finally find more. In other cases, it doesn't happen very fast at all, and it's you don't have any environmental problems from it. So, I mean, if you did a static test on a well-crystallized rock that had pyrite that had a lot of well-crystallized rock, you might say, well, this is going to be a real acid generation problem, but for whatever reason, it doesn't oxidize very fast. So it isn't. And that's why lab bench tests aren't very good for predicting what is really going to happen. So next slide, please. Well, that's it. So, so if you have any questions, please send them in. And I hope you enjoyed the talk.